This video marks a significant shift in our modeling focus from normal linear regression to logistic regression. Consider a motivating example. In the data shown here, each row represents a mountain climber that has participated in an expedition to summit a Himalayan mountain peak. For example, in the second row, a 27-year-old climber that did not use supplemental oxygen tried to summit Mount Everest, and they were not successful. This data then sparks some questions. To what extent does a climber's success Y depend upon their age, or whether or not they use supplemental oxygen? Or how does it depend on the height of the peak they're trying to summit? Thus, in this analysis, a climber's success is our response variable, and factors such as age, oxygen use, and peak height are potential predictors of success. Consider the following model of the trend in success versus age alone. Though we see a model table, it's not very clear how to interpret the coefficients. For example, consider the age coefficient. Does it make sense to say that for every extra year in age, success decreases by 0.0055? No. Our response variable success is categorical. A climber can either be successful or not, but nothing in between. To illuminate this modeling mistake, check out a visualization of our model. On the y-axis, the outcome for each climber is encoded as 1 or 0, success or failure. The points are just shaken up here or jittered a bit so that one data point doesn't hide behind another. Now what our model is doing here is trying to model these 0-1 categorical outcomes using our same old modeling tools, and the result is clearly goofy. The model trend lives in a world in between the possible 0-1 outcomes, simply missing the mark. Now, if the climbing example here were an anomaly, we mightn't care so much, but binary or two-category response variables are quite common in practice. In our example, we wanted to model whether or not a climber succeeds, yes or no, by potential predictors such as age, oxygen use, and peak height. Similarly, we might want to model whether or not somebody votes by potential predictors such as age, politics, political engagement, how accessible voting is in their county, and so on. Or a spam filter tries to predict whether or not an email is spam by factors such as word usage, whether or not the sender is in the receiver's contacts, and so on. In general, examples of pass, fail, yes, no, true, false, and other binary responses abound. So imagine this. You sit down to a meal of bread and soup. To cut the bread and eat the soup, you need the right tools. It's the same thing in statistical modeling. When modeling a quantitative response variable, normal linear regression, that is the modeling that we have been doing, is often an appropriate tool. Yet when modeling a binary categorical response variable, we need a different kind of tool, logistic regression. To set this up, we'll write our binary categorical response variable y as 1 or 0, 1 if the event of interest happens and 0 otherwise. For example, y is 1 when a climber is successful and 0 when they're not. But instead of modeling the raw 0 and 1 outcomes, as we tried and failed to do in the intro to this video, we'll instead model the uncertainty in y. To this end, consider 3 measures of uncertainty, all of which communicate the same information, but on different scales. These are the probability of the event, the odds of the event, and the log odds of the event. Then the goal of a logistic regression model is to model the behavior or uncertainty in y by one or more predictors x. Notice here that the right side of the trend equation is the same. Beta 0 plus beta 1x. Now what we have to think about and what's different here is how to measure uncertainty. So the part of the model equation on the left. To begin, suppose we were to model the probability of the event by this linear trend. So modeling P by this linear trend. Now, this would be a mistake. Recall that a probability is restricted to be between 0 and 1, yet the model trend can extend beyond this range, leading to nonsensical results. For example, this model might produce probability predictions that are either negative, down below our appropriate range, or predictions that are above 1. In short, this approach is wrong. Next, suppose we were to model the odds of an event by this linear trend. Now this too would be a mistake. Recall that the odds are restricted to be above 0. Yet the model trend can extend beyond this range, leading to nonsensical results again, such as negative odds predictions. So again, this approach is also wrong. Finally, suppose we were to model the log odds of an event by this linear trend. This is not wrong. Like the trend line, log odds can take on any value, from negative to positive infinity, thus assuming that there's a linear trend in the relationship between log odds and the predictor x doesn't violate any fundamental truths about log odds. Now this is great. Via log odds, we now have a not wrong approach to modeling the uncertainty of a binary categorical response variable y by predictor x. Yet for most people, myself included, a log odds model might not be wrong, but it's also not very useful. Mainly, it's tough to interpret log odds. But never fear. Remember that we can translate log odds to the odds scale through exponentiation. Now when we take e to the log odds and get our trend line, or trend curve now, e to the beta 0 plus beta 1x, that we now have a non-linear trend. So the model that was linear on this log odds scale is non-linear on the odds scale. And consistent with the properties of odds, this non-linear trend is restricted to be above 0. We can further translate this model on the odds scale to the probabilities scale by dividing the odds by odds plus 1. On the probability scale, this model takes on an S shape, which, like probabilities themselves, is sandwiched between 0 and 1. In conclusion, though they look quite different, these three model trends provide the same exact information about the relationship between a binary response variable y and predictor x, just on 3 different scales. Our next step will be to make meaning of these models. For example, though we can interpret our model coefficients as usual when working on the log odds scale. For example, beta 0 and beta 1 are still an intercept in slope. Those beta 0 and beta 1 coefficients manifest differently on these nonlinear odds and probability scales.